In the last class, we saw something about MOSFET and its characteristic. We started with a wafer. This kind of thing is called a wafer, okay. Maybe hundreds of microns thick it is. You start with, let us say, p-type wafer, p-type substrate you call, whatever is used for fabrication of IC, the basis, the base material, that is called substrate. So, p-type substrate you start with, let us say. Then we diffuse n-type impurity into this. So, these are n regions, these are n regions. N regions. One is source, another is drain. These are isolated because normally if it is p-type substrate, okay, this is connected to the most negative potential of the circuit. In any IC, okay, if it is starting with p-type substrate, the substrate has to be connected to the most negative potential, because all the devices are isolated by a junction, okay, which is substrate and the particular material where the device is fabricated. So, we have a junction here, okay. So, this is always connected to the most negative potential, so that when the signal is applied, okay, under no circumstance will it go ever to positive bias situation, okay. So, the isolation is maintained. So, in this case of a MOSFET also the substrate, if it is p substrate, it should be connected to the most negative potential. If it is n substrate you are starting with, it has to be connected to the most positive potential in the circuit in an IC. So, this is the basis of any design. So, please remember that, because in all these ICs we have a substrate, and depending upon the type of substrate we are connecting it either to the most positive potential, okay, or most negative potential. If it is n type substrate you are starting with, then it is connected to the most positive potential. If it is p type substrate, it is connected to the most negative potential. Now, that is in this particular case also called body, that is why we call it as B, okay. This is body, this is source, this is gate, and this is drain. As I told you, for biasing this, to make these devices come into the active region, we need supply voltages, and we would like to make use of minimum number of supply voltages. So, body and substrate, the source, okay, has to be reverse biased. The best way of reverse biasing, of course, is connect zero bias, which does not need any source. Any other biasing will require a voltage source. So, here the bulk or the body or the substrate is connected to the source, right. Now, if you do not want to do it, then you have to take care that there is a DC potential applied here, so that this is negative with respect to the source. That is all that you have. Now, if that is done, we have now 3 terminals, okay, for the MOSFET. That is why you have the symbol here. Let us try to understand the symbol for the MOSFET. Gate is insulated from the parent material where the channel exists. So, that is the gap. Then we have the source and drain isolated from, okay, this is this channel. This channel can exist only if I apply a voltage. So, this break indicates that this is an enhancement type, otherwise source is not connected to drain normally. So, the break indicates that unless I apply a voltage, the channel cannot be formed, okay. So, this is the symbol. Now, as far as this arrow is concerned, let us also understand why this arrow has come about. This arrow, as I told you, in any symbol in electronics indicates always the actual direction of flow of current, but current need not flow. Okay. This actual direction of flow of current when that particular junction, okay, near that is forward biased, okay, but the junction normally may not be forward biased at all. In this case, let us say this is the bulk or the body or the substrate. So, look at the substrate, it is P, and when this is going to form a channel, it will become N. Okay. So, P to N always arrow is indicating the actual direction of flow of current, P to N, whether it is a diode or a transistor, always from P to N the arrow is marked. Okay. Is this understood? Whether it is a bipolar transistor, okay, or a MOSFET or a diode, from P to N always the direction is of the arrow is marked. So, that will sort of make you remember how to remember the symbol for each of these, right. Now, this is a pretty complicated symbol for drawing by a draftsman. Okay. It requires patience, okay, to break this and all. We do not want to waste time, okay, precious time in drawing a fairly complex circuit, maybe an integrated circuit, VLSI and things like that. So, we do not want to waste our time in taking care to see that it is an enhancement type, therefore, there is a break and all that. For that, a simple symbol is going to be resorted to. This is the simple symbol adopted for a MOSFET which is N channel enhancement type. Why? Now, if okay, this is connected to positive potential, this also is going to be connected to positive potential for making it work. The current direction will be always this way, and the current direction is always marked at the source end or emitter end. Okay. So, the current direction is indicated here this way. Right. So, this is the source end. So, indicate the current direction at the source end. So, all this business about substrate is forgotten there. Okay. It is assumed that the substrate is connected to the source, okay, and you are shorting this. So, with the resultant effect, this is the simplified symbol for a MOSFET which is now universally adopted. Okay. Now, obviously, the biasing for making it work is positive with respect to source. You apply a positive voltage here as well as to the drain, then only MOSFET action occurs. Let us sort of briefly review what we understood in the last class quickly. I told you there is no connection between source and drain, that means the resistance between source and drain is infinity as such. So, that is enhancement type of MOSFET is normally that is normally open kind of thing. Then in this sort of not switch is, if you are using it as a control switch, it is normally open switch, control switch. So, if I plot IDS, okay, versus VDS, IDS is the current here versus VDS, okay, voltage VDS. Let us see how it looks like. Obviously, the resistance is infinity, that means there is no current, okay, whatever be the voltage VDS. So, this is the characteristic curve. For VGS equal to 0. Okay. So, for VGS equal to 0, this is the curve. No current. Now, that is because there is a junction formation here, okay, and even if I apply more VDS, VGS equal to 0, okay, even if I apply more VDS, okay, the depletion layer width keeps on increasing and there is no question of any current. This reverse bias here keeps on increasing and this, right. Now, when VGS becomes equal to VT, we have defined this as a threshold voltage, which is an important voltage. What is that voltage? It is that voltage at which there is, when you apply a certain voltage with respect to the source or the body, there is a what? Channel formed. That means, as I told you, as I apply a positive voltage, the P substrate contains lot of what? Mobile carriers, which are what? Electrons as well as holes. Electrons are the minority carriers, holes are the majority carriers. Electrons tend to come towards the surface, right. So, and the holes are repelled if I apply a positive voltage here, okay. So, this side becomes less P type. Suppose this is P plus, this becomes just P type. That resistivity of the surface increases. This is what first happens. Then as further positive voltage is applied, you have most of the, let us say, minority carriers already coming to the surface, then you are starting to uncover, okay, the immobile, okay, atoms which are charge carriers, okay, carrying what charge? Now, the impurities here, okay, donate a hole, therefore acquire a negative charge. So, that way the negative charge is uncovered here. That means this region gradually becomes depleted of carriers, okay, and then slowly you further increase the positive voltage there, right. Then the surface becomes, okay, what? Flooded with minority carriers which are electrons and the type becomes N type. Then you say that there is inversion, okay. So, now once inversion occurs, a channel is said to be formed and this depletion layer is pushed down. Okay. So, this is how the channel gets formed and the voltage that you apply to the gate to make a substantial amount of current flow, okay, start flowing, okay, is called the threshold voltage. So, when you apply the threshold voltage, the channel is just formed, let us say very thin layer. That means the resistance is still very high. Current is going to flow, but very, very small. So, current has started flowing. So, for VGS equal to 0 to VGS equal to VT, we have still, okay, current flowing here, but very low. That means resistance can be still considered very, very high. Now, I apply further gate voltage with respect to source, which is greater than VT. That means additional voltage that I have applied is VGS minus VT extra. Let us say this is what you have applied. Corresponding to this, the width of this is going to increase. If VGS minus VT is, let us say 1 volt, there will be certain channel width. If it is 2 volts, the channel width will be more. If it is 3 volts, it will be still enhanced. This is why it is called enhancement type of MOSFET. The channel width can be enhanced by applying suitable voltage to the gate. So, once you enhance the gate that is channel width, let us see what happens. As long as VDS is still 0, it looks just like an ordinary resistor. The width is uniform throughout. VDS is 0, so VGS and VGD remain the same, and therefore the width here is uniform. So you can treat it as a plain good old resistor, okay, of a certain width in this direction, certain depth here, okay, certain length. So the width is in this direction, okay, length, channel length is in this direction, okay, width is in this direction, okay, and there is a certain depth determined by what voltage you are applying in excess of Vt to the gate. Okay. Now, this is crucial in determining the depth here. So, depending upon this, if this magnitude is higher, okay, this depth would be higher. Therefore, what can we conclude about the resistance now? That the resistance keeps on decreasing as I apply higher and higher value of VGS. The resistance keeps on decreasing. That means this is really equivalent to, this channel is really equivalent to a resistance as long as VDS is kept close to 0, okay, this uniformity of this resistance depth can be stuck to. So, I can therefore say that for a certain value of VGS minus VT, this is it, and for a certain other value of VGS minus VT, this is the characteristic, right. VGS minus VT going on increasing, right. So, this kind of characteristic is followed. That is why this MOSFET can be used as a voltage dependent resistor or voltage variable resistor. It is called voltage dependent resistor or voltage variable resistor. Now, obviously, let us look at this channel here. What happens when I connect a voltage like this VGS we have discussed. Now, what happens when this voltage is increased? Right. This is VGS, okay, and I have been able to open up a channel whose width corresponds to VGS minus VT. Now, the voltage between G and D was same as G and S when this was shorted. But now, I am applying a voltage, if you see from G, this is VGS, VGS minus this voltage is what is applied to D. This is opposing this, right. So, what should happen to the channel width? It should decrease. At the drain end, it will start decreasing as I start increasing my value of VDS. So, because this VDS is opposing VGS in forming the net VDG, right, the channel width will decrease. What is the value of VDS that I should apply to close the channel? That is same as VGS minus VT in the opposite direction. Right. That point at the channel gets closed at the drain end is called the pinch off point. The channel is pinched off, right. So, what happens to the channel? Let us depict it in a sort of neat manner. Originally, let us say that it was like this. This is the channel. As I apply, okay, higher and higher, this is for a certain value of VGS minus VT, let us say VGS1 minus VT, we will call it. This is the channel width. This width depends upon this value. Now, as I apply more and more value of VDS, this remains the same, nothing has changed here. Okay. This width corresponds to simply VGS minus VT, whereas VDG is changing because VDS is increasing. Therefore, this width here on this side will decrease. This is what happens. This is for a certain value of VDS. So, this resistance, strictly speaking, is nonlinear because we are plotting ID versus VDS. The width or the depth of the resistance itself depends upon VDS. So, this is a nonlinear resistance. What happens to the resistance we can understand, because the width uniformly, that is the depth uniformly decreases. So, effectively the incremental current for an incremental voltage should keep on decreasing. An incremental current, because now it is a nonlinear resistance I am talking of. So, an incremental current for an incremental voltage remaining the same will keep on decreasing. Okay. That means, okay, for the next portion of the incremental voltage, the incremental current is going to be less. This, okay, same voltage if you maintain, this current is going to be lesser than this current, and the next current is going to be still less. Ultimately, at the pinch off point, what is the pinch off point? VDS equal to VGS1 minus VT. At this point, VDS equal to VGS1 minus VT, there is this channel getting completely closed. So, we can say that this is the position for VDS, okay, equal to VGS1 minus VT. So, current is said to reach its saturation value at this point. For a lower value of VGS minus VT, obviously the saturation occurs at the lower value of VDS. Okay. And for VGS, okay, equal to VT, saturation occurs at this point itself and the current is 0. So, these are all the points at which pinch off occurs. This terminology should be very easily remembered, okay, because that actually depicts what happens at the channel, okay, pinch off. So, this characteristic is understood as FET characteristic, and the transistor, FET transistor, okay, field effect transistor, is operated in the current saturation region. This is called current saturation region. This region, below this region, is called triode region. Okay, this region. This is called triode region, and this region where the current goes to saturation is called current saturation region. Let us therefore now mathematically indicate what this is. ID yes was equal to, okay, some proportionality constant, okay, will put it as 2k. We will see why that 2k is put. Some proportionality constant, k dash you can call it, that k dash is 2k into VDS, okay, into VGS minus VT. So, it is understood that IDS depends upon VGS minus VT. Okay. Why? Because the channel width depends upon VGS minus VT. The conductivity increases as VGS minus VT increases, right, or resistivity decreases. So, it is dependent upon VGS minus VT. Higher current will be obtained, higher the value of VGS minus VT. So, the proportionality constant depends upon VGS minus VT, and it is a resistor. So, it is directly proportional to VDS. So, IDS by VDS is equal to 2k into VGS minus VT. Okay. So, this is called the FET resistance, RDS. In the triode region, or actually in the region where it is linear, where the nonlinearity has not yet come to picture. Now, in this region therefore is perfectly linear, but thereafter we have, okay, nonlinearity setting in. What is that nonlinearity? It is called square law nonlinearity. That means some current is going to be reduced, right, and the reduction is dependent upon square of VDS. So, actually if you see here, since it is square, right, so it is going to be here adding on to the current, right, because VDS changes polarity, VDS square does not change polarity. So, here, okay, it is getting reduced, here it is getting added, because VDS square polarity remains the same, VDS polarity has changed here, right. So, this is the nonlinearity that comes into picture. Therefore, this region it is not suitable, okay, it never goes to saturation, the current never goes to saturation, it is increasing. Okay. So, in this region it is not suitable for FET action, third quadrant. It is suitable for FET action only in the first quadrant. Okay. So, that is the nonlinearity, and therefore, it no longer is a linear resistor as depicted here. This formula is not valid because it is nonlinear. Okay. And this keeps on happening, okay, until we reach a value of VDS which corresponds to VGS minus VT. That region is the region of what? Pinch off, where the channel is closed completely, where the current just starts getting saturated. So, you can substitute the value of VDS in this expression, that should give us the value of current saturation. Okay. So, substitute this, VDS is equal to VGS minus VT, thereafter it is independent of VDS. Current has reached saturation, what it means is it is remaining same whatever be the value of VDS. So, substitute the value of VDS there and you get IDS equals, okay, K into VGS minus VT whole square. So, please remember now these simple equations which will depict the entire region of operation of the field effect transistor. Simple equations. This is what is called square law equation. Okay. K is dependent upon W by L ratio. Okay. You know, W is the width of the channel and L is the length of the channel, and the resistance of the channel obviously depends upon W by L. It is directly proportional to W, it is inversely proportional to length. Okay. So, the K is a factor which is dependent upon W by L ratio. Okay. Obviously, it depends upon the mobility of the carrier, etc. If it is N channel, it will depend upon the mobility of electrons. If it is P channel, it will depend upon the mobility of holes. Okay. More than that, we are not interested in learning as far as this equation is concerned. So, it is enough if you understand the regions of importance. Once again, this is the triode region where it is linear and then there is a square law getting subtracted, and at this point it is pinch off, and beyond pinch off it is current saturation, it is equal to this. Now, this is similar to transistor current going to saturation here, okay. But only one difference, that it is not true that this current is really independent of VD. Yes, just as we had early effect discussed in the BJT, where this current was still dependent upon VCB. Okay. Here we have this current not really independent of this VGS, VDS, VT squared into 1 plus, okay, let us say lambda times VDS. The dimension of lambda is 1 over voltage, okay, 1 over some voltage, right. So, this is what really happens in the case of a practical field effect transistor. It is not all that independent, there is certain amount of dependence. Okay. It is not going to remain constant at this value of K times VGS minus VT whole squared, it is slowly increasing. What again this means is that this dependence is going to sort of, if you extend it, it will get in, the intercept will be somewhere on this axis, right. So, that is what is 1 over lambda. Okay. If you find out the intercept along this line, it will be corresponding to 1 over lambda. So, this characteristic is exactly identical as far as the P channel enhancement type MOSFET is concerned. Let us understand the difference. In the P channel MOSFET, okay, we have to have either N type of substrate, and then this will be P, and this biasing will be negative with respect to source, and this biasing will be again negative, right. And therefore, the threshold voltage itself is going to be negative. Okay. The point at which the channel gets formed is itself negative. So, except that the other discussions remain the same. The symbol, obviously this arrow, okay, is going to be in the opposite direction. So, negative, negative, right. So, this is for P channel. Enhancement type of MOSFET. Of course, we can have both N channel and P channel coexisting in an integrated circuit. Let us say we start with P type substrate, then these will be N type of source and drain, then we have an N channel, and I would like to have, let us say, a P channel FET also in this, then I will have an island of this diffuse region to formulate a P channel FET, in which I will now diffuse into this what? P type impurities source and drain, and then we will have again similar gate like this. This is silicon oxide, which is also there here as the gate oxide, and then over this we will have the contact source and the drain contact, and we have the gate contact on this. So, now, so we have this N-type material here, P-type diffusion occurring in this N-type material, and we have source, gate and drain. So, in the same wafer I have what? N-channel MOSFET as well as P-channel MOSFET. This is called CMOS, complementary MOS. Okay. This technology of fabrication of this kind of thing is called CMOS technology. You can have a technology where we do not have this P-channel at all, we have only N-channel MOSFETs throughout. So, you can have N-channel VLSIs or P-channel VLSIs or CMOS VLSIs. These are the three different technologies which are available for fabrication of very large scale integrated circuit. Okay. Advantage of course in the previous one of N-channel or P-channel is that okay, the number of steps are less. Here the number of steps of fabrication are more. The more the number of steps, the less reliable the system becomes. Okay. The more the number of times the human beings start interfering, okay, the less reliable the system becomes. This is always the general truth in any system. Okay. So, therefore, the reliability depends upon the number of steps. Okay. The yield also depends upon the number of steps that you adopt for fabrication. So, most of the VLSI circuits okay, can be either N-channel okay, alone being used, NMOS technology or PMOS technology or CMOS technology. Okay. To this same category of field effect transistors belongs another type called junction field effect transistor, junction field effect transistor, popularly known as JFET. Let us see how it looks like. We have, let us say, the same type of substrate, P-type substrate, in which now we have N type of diffusion done, and then later on P-type of diffusion done again. And the second P-type diffusion corresponds to the gate. Right. So, the metal contact is placed over the gate. Here we have source and here we have drain. This is the N channel. This is the N channel. It is already linked. Source and drain are already connected. So, this type of FET is called depletion type of FET, because there is already a channel. You can close it only by depleting carriers okay, from this, or actually extending the depletion region further into the channel. Right. So, the source and drain is already connected, unlike the other FET which is called enhancement type of MOSFET, where source and drain were not connected. They could be connected by only applying a voltage. Here it is already existing. This is a resistor, plain resistor. Between source and drain there is a certain amount of resistance depending upon the doping of this N channel. Okay. Now, how do we really sort of make this a field effect transistor? Obviously by pinching off. So, please remember this pinching off is the characteristic of a field effect transistor to work in the active region. So, now let us say here for VGS equal to 0, the channel width is, that is depth is going to be this much. Okay. Let us assume that this is the channel length and there is a certain width here. The depth here is going to be fixed by the extent of reverse bias applied between gate and this source. If VGS is 0, that is going to be a normal depth. That means this particular thing is going to be a plain old resistor for VGS equal to 0. Then once I start applying VDS, what should I do? In order to close this channel width here, I have to extend this depletion layer width here. So, please remember this is N and let us say this is, we are starting with, how do we reverse bias this junction? This is a junction here which is important, which should be always kept reverse bias so that the gate does not start conducting. Gate is P type and source is N type. So, if I apply a positive voltage here with respect to this, this will start conducting. That means this should be biased in the opposite direction. So, that initially there is no gate current at all, right. So, please remember for the same N channel MOSFET, we had to bias it with positive voltage. That is because we wanted to cause a channel to exist. Here the channel is already existing, right. So, in this particular case, as far as the gate is concerned, it must be always reverse biased with respect to this source, right, so that the gate current is not drawn. That there was no problem. Gate was insulated from the channel by a silicon oxide layer. We could bias it positively or negatively, strictly speaking, right. No current was going to flow. Only thing is, in order to cause MOSFET action, we had to bias it with positive voltage in the case of N channel. So, this is the kind of voltage. If I apply more voltage, this depletion layer width will increase and the channel width will decrease. That means the more reverse bias voltage, that means this is made more negative, then we have this going like this. So, this depletion layer width is going to increase and channel width is going to decrease, which means there is a specific voltage at which the depletion layer width will cover the entire channel, and that is called the what, which we have already defined. Whenever the depletion layer width covers the entire channel, that voltage is called the pinch off voltage. So, here the only voltage that is important is the pinch off voltage, right. So, since the channel already exists, right, the voltage that you apply to the gate for closing the channel is called the pinch off voltage. That means at this particular point, right, you are applying a VGS which corresponds to in magnitude equal to the pinch off voltage. Right. This corresponds to that. There is therefore no connection between source and drain, and the current is 0. So, this is let us say VGS equal to 0 and VGS more negative, and ultimately magnitude of VGS being equal to some value called pinch off value. Okay, it is a negative value in this case. Next, if that is the case, for a given value of VGS here, it is having a certain channel width, okay, and the channel width is going to decrease as VGS magnitude is increased. But now when I apply a value of VDS, now you see, why did I apply this polarity? Because for a given value of VGS this way, I would like to close the channel at the drain end. That is possible only if these things add. Okay. So, this voltage will add on to this voltage, and therefore, effective reverse bias voltage at the drain end is increased in magnitude. Okay. So, for a given value of voltage VGS, let us say equal to minus 1 volt, minus 1 volt. What is the value of VDS that I have to apply in order to close the channel? Have you understood the problem? Okay. VGS equal to minus, okay, we will say VGS equal to 0 volts. What is the voltage VDS that I have to apply in order to close the channel here in magnitude? Pinch off voltage, right. So, that by definition is the pinch off voltage. Pinch off voltage when VGS is 0, the VGD, okay, is the same as VSG, right, VSD, right. So, the voltage that I have to apply to the drain in order to close the channel when VGS is equal to 0 corresponds to pinch off voltage in magnitude. So, if you say pinch off voltage magnitude is 3 volts, okay, and VGS is minus 1 volt. What is the value of VDS at which pinch off occurs? Minus 2. If VGS is minus 2 volts, okay, what is the value of VDS at which pinch off occurs? Plus 1 volt, right, because pinch off voltage, okay, essentially remains the same, it is 3 volts, right. Whether it is getting distributed between VGS and VDS is your affair, right. So, let us now see. The same thing happens, this is a nonlinear resistor here, and this will keep on decreasing, and at a value which is equal to what? VDS equal to pinch off, it goes to saturation, the current remains constant. And let us say this corresponds to VGS equal to minus 1 volt. Okay. So, at VP VGS equal to minus VP minus 1 volt, okay, this will go to saturation. Okay. Let us say VGS equal to minus VP, right, then VDS equal to 0 itself, pinch off occurs. So, this is the kind of pinch off characteristics, right. So, characteristic is exactly similar to that of MOSFET characteristic, but this mode of operation is called depletion mode. This mode of operation is called depletion mode. You can actually build a MOSFET also equivalent to this by having a channel. Okay. So, you can also have a channel, you can have N, okay, and the gate oxide and diffuse impurity here, okay, diffuse impurity here, and actually have a channel like this, and then have a gate oxide here, and then have source and drain. This type of MOSFET is called depletion mode MOSFET, even though it can work both in the depletion mode and enhancement mode, because it is a MOSFET. Okay, we can apply positive gate voltage or negative gate voltage, nothing is going to happen. Okay, it will not draw any current. So, as far as the depletion mode MOSFET is concerned, you can have a channel already existing, that means the symbol is very clear, right. The channel is already there, so it is not broken, okay, and this is the substrate. Okay. So, this is the complete symbol, but again this is too cumbersome for us to draw. Okay. So, like the other case, the symbol, but then you indicate, okay, saying that this is already having a diffused channel. Okay. This shaded portion indicate a diffuse channel already existing. This is called a depletion type of MOSFET. So, depletion type of MOSFET and JFET, okay, have similar characteristic. Okay. But depletion type of MOSFET can also be worked in the enhancement mode of operation. Okay. So, basically the equation is also the same square law, but instead of having K and all that, you have this as IDSS constant 1 minus VGS by VP whole square. It is same square law. Mathematically there is no difference between the equation that I have given for enhancement type of MOSFET and this. Only the constant of proportionality I am defining it differently. What is that constant? That constant corresponds to the current saturation for VGS equal to 0, because there is a characteristic corresponding to VGS equal to 0 here. Okay. Whereas in the case of enhancement type MOSFET, there is no such characteristic called VGS equal to 0, because the current is not yet flowing. Only when voltage exceeds, okay, the threshold voltage, current starts flowing. So, in this case the same equation is rewritten as IDS. For example, this can be IDSS, okay, by VP into VP minus VGS whole squared. Okay, since it is squared, this is VP squared, IDSS by VP squared into VGS minus VP whole squared. See, this is similar to K into VGS minus VT whole squared. Okay. Only thing is K is defined differently, okay, in the case of depletion type of MOSFET or JFET. So, it is always defined this way, saturation with respect to saturation current at VGS equal to 0. So, characteristic also is mathematically the same as that of enhancement type of MOSFET, mathematically. Okay. So, with this we stop discussion about the FET characteristic. In the next class we will discuss about the FET circuits.